just understanding the whole definition of Riemann sum. Just kind of reminding ourselves what we do in 5A and doing this as a double sum. So I don't have the answer to number 14 with me. Does somebody want to give me what they got, or if they checked it in Slater or something? Anybody? Oh, is that a picture? It was a graph? I somehow remember the sticky note in my book. So it is 9 minus y squared over 0 to 4 and 0 to 2. So x goes from 0 to 4, where y goes from 0 to 2. So the domain is this rectangle. And 9 minus y squared is a parabolic cylinder. So we'd be looking at something like this. Except for just the piece of it that is over that. So if we put in 2, we get 5, so we go up here to 9, here we get z equals 5. We get something like this. Same thing here, something like this. Okay, not very good picture, but it's z equals 9 minus y squared over that rectangle. Okay, anything else in 15.1? You got the idea there? Okay, 15.2, the extra question that I gave you, the point of that one is kind of to remind you how in Math 5A when you were finding integrals and area, how you could look at it with respect to x or y. So that was the point there. Let's go ahead and see it. Okay, so it was find the area bounded by y equals the square root of x. So y equals the square root of x, and y equals 6 minus x. And the x-axis. Yeah, and then it got cut off there. I don't know if you got the whole instruction. So the idea was if in Math 5A I asked you to find the area of this region here, we could do this two ways. We could either integrate this with respect to x. If we integrate with respect to x, we'd have to break it into two pieces because that top curve changes. So we would have to go from 0 to, I'm thinking double integrals here. We'd have to integrate radical x from 0 to this point here, and they intersect at the point 4, 2. So we'd have to go 0 to 4, the square root function, plus, and then 4 to 6, 6 minus x. Okay, so it's just trying to get us to remember how to do those. And then if I went dy, then we'd be looking at what y does. And y goes left to right, black to green. So it would be green minus black. If I solve this for x, I would get 6 minus y. So it would be 6 minus y minus the black function. And the black function is y equals the square root of x, which is x equals y squared. So minus y squared dy. Y goes from 0 to 2. Okay? I don't have the answer. Does somebody have the answer for that? If you want.
My answer is 22 over 3. I don't even know
Yeah.
if it's
22 over 3?
I saw that 22 over 2.
So that was just trying to get you to remember to kind of be looking at things from both directions so that when you get to double intervals, it's kind of the same thought process.
But can we do like double integral?
Yeah, so if you were going to do this now that we have double integral, if you're going to find the area using a double integral, this is kind of that graphic that I gave you, or the table that I put up here. You have to be careful. If you're finding area using a single integral, you're integrating a function. If you're doing area using a double integral, whoops, you're integrating 1. Okay? So if you're going to do that, and you wanted to do it as a double integral, then you can go dy dx or dx dy. And so let's suppose that we did this, let's go dx dy first, we can look at the other if we want to. So what we would do for x is we go, okay, well x goes from, and it was the left curve, which is 6 minus y, to the right curve, which is y squared, as y goes from 0 to 2. That's how you'd set it up if you're going to set it up as a double integral. And if you notice, like if we take the very first step, if I integrate this with respect to x, I get an x. Evaluated here would be y squared minus 6 minus y dy. So in one step, we'd be to write, whoops, I must have done something wrong. What did I do wrong? Left to right. Oh, I got these backwards. The left-hand graph is left to right. So the left graph is y squared, and the right graph is 6 minus y. So this is the other way around. Okay? So, are you videotaping all of this? Or
Yeah, they want me to do it instead of for
okay,
class.
can you give me a link too so I can give it to the other class?
Yeah.
Great, thanks. Okay, so I haven't done one like this with you guys where you can see, when you first learn this, it's like, oh, cool, we can do all these with double integrals. It really is the same amount of work either way, okay? But you just have to remember that if you're going to do a single integral, you're integrating some function. If you're doing a double integral, you're integrating the function 1. Same connection for triple integral for volume, you'd be integrating 1. Double integral for volume, you're integrating the function. Same idea. All right. Anything else from 15.2? Okay. I'm assuming we're going to be spending a lot of time with triple integrals, but we need to look at the other stuff too. So 15.3. In 15.3, that's where we're learning how to set up double integrals. Yeah, so 49. Oops. Okay, so 49 is double integral 0 to 1, 3y to 3. E dx squared dx dy. Okay, so I can see the instructions, but I'm ignoring them for a second, okay? So let's suppose you were given this integral, because I won't typically tell you to reverse the instruction, reverse the direction. So I'm looking at this and I'm trying to figure out how to integrate this with respect to x, and I can't. Hopefully you recognize that. That's kind of one of the classic examples of something that you can't integrate in closed form without using infinite series or anything. So I'd be stuck. So what I'm thinking is that we should try reversing order. Now to reverse order, what I would do is recreate the domain. I know some of you do this all algebraically. I like to do it geometrically, like drawing a picture. So x goes from 3y to 3. So x equals 3y is the same as y equals 1/3 x. So that's kind of not as steep of a line. And x goes from there to x equals 3. X equals 3 looks like this. So x goes from here to here, left to right. As y goes from 0 to 1, well, it just so happens that this, when y is 1, x is 3, so this is the point 3, 1. So this is the domain here. Okay, so that's what I mean by recreating the domain. Now to set this up, e to the x squared dy dx. And y now, we're looking at it this way. Y goes from the bottom curve is 0 to the top curve, which if I solve for y is 1/3 x. So y goes from 0 to 1/3 x as x goes from 0 to 3. Okay, questions on how that works? Now you might look at that and go, well, you still have to integrate e to the x squared. Yeah, I don't know how to do that, but I don't have to do that yet. At least I can put it off a little bit. So I'm going to integrate with respect to y, and I get y e to the x squared as y goes from 0 to 1/3 x. And then I'm still going to have to integrate that with respect to x. Putting in 1/3 x minus what I get when I put in y equals 0, which is 0. Okay? So now I don't just have this e to the x squared I can't handle anymore. Because of this extra factor here, I can do this by u substitution. If I let u be x squared, then du is 2x dx. And so x dx right here is du over 2. So I would have this 1/3. I have a factor of 1/2 from here. And then x dx is du. And e to the u. Okay? We can switch to use limits, or go back and put it in terms of x at the end. If I switch to use limits, when x is 0, u is 0. And when x is 3, u is none. So I get 1/6 e to the u from 0 to 9, which is 1/6 e to the 9th minus e to the 0, which is 1. Okay? There's usually one on the test where you have to reverse the order, but I don't necessarily tell you like they did. You would be looking at something that you maybe got stuck on, integrate, and go, I can't integrate that, what could I do? When you can't integrate something, try a different order.
You're not going to say you need to solve this integral and have dy dx. Like, I guess because of triple integrals, I'm going to assume that you have that order for a reason. Like, that's how you need to solve it.
Oh, well, there's one problem in particular I'm thinking of that I said, set it up this way, and then integrate it whichever way you want. So you could pick one of the ones I chose, you could come
So
up
you,
with
I mean, you
smart.
say that though.
Yeah.
Integrate however you want.
Yeah. But on one like this, like if you look on the sample test, I think there's a problem like this where I just say, find this value of this integral. And I don't tell you to switch order or anything. So you're not stuck doing it that way. You can change the order. You only have to do a certain order when I say, set it up in this order. All right, 53. 53 is right here also. So we're integrating with respect to x first, and they tell us on this one. This one might be a little bit less obvious that you're going to have trouble integrating it this way. I mean, if I didn't tell you on this one, I'd probably try use substitution or something, but you're going to get stuck. But they told us on this one, and if I gave you one like, if I give you one like an e to the x squared or a sine of x squared, something like that, you should know pretty quickly that you're going to be stuck. I'm not going to give you one like this where you could spend 15 minutes on it before you realize you're stuck. Okay? All right, so they asked us on 53 to reverse the order. So x goes from arc sine of y to pi over 2. Okay, x equals arc sine of y equals x is the same thing as y equals the sine of x. And, if I said it's the same thing, if you had me for a trig, you'd know that, or for 5b, you'd know that I'm kind of picky about this. These are not exactly the same. They're only the same when y is between 0 and pi over 2. X is between 0 and pi over 2. But anyway, so we have y equals the sine of x, so like this, between 0 and pi over 2. Alright, so x does what? It goes from the left, this curve, to the right, pi over 2. There's pi over 2. So x goes from the left, from the curve y equals the sine of x, or x equals the arc sine of y, to here, which is x equals pi over 2. While it's doing that, y goes from 0 to 1, which means it does this whole region. So this is my region. Okay? So if I'm going to turn that around, then I would have y going from 0 to sine of x as x goes from 0 to pi over 2. Cosine x, radical 1 plus cosine squared x, and this is dy dx. Okay, questions on that? That arcsign sometimes gets people. Now if I'm going to integrate this with respect to y, I will just get a factor of y, and I evaluate it from here to here. It's going to end up giving me, kind of skipping some of that middle work, let me know if you need to see it. That'll give me a factor of sine of x. Okay, now it's a pretty straightforward u substitution now that I have that sign there. If I let u equal cosine, then du is minus sine. And so this will be radical 1 plus u squared. Cosine is u. Sine of x dx is a minus du. Okay? When x is 0, cosine of 0 is 1. And when x is pi over 2, cosine of pi over 2 is 0. I guess I could have done this all in one step. Actually, I could have done a better use substitution. Do you see it? What I could have done?
Yes.
Yeah, if I let, we can still do it from here, but if I let u equal 1 plus cosine squared of x, then du would be 2 times the cosine of x times minus the sine of x dx. And so this would be radical u, and then sine x cosine of x would be negative 1/2 du. That would be better. We're okay here. We're just going to have to make another substitution. So if I let v equal 1 plus u squared, then dv equals 2u du. Okay? You're okay from there? Yeah? Let me know if you're not. All right, 48062. In evaluating a double integral over a region D, you get this integral, sketch the region, and express the integral as an iterator. Okay, so they're just asking us to reverse the direction. It's a useful skill, and it extends to triple integrals as well. All right, so what have we got? We've got x goes 0 to 1, 0 to 2y. So 0 to 1, 0 to 2y, f of x and y, dx, dy. Okay, so x goes from 0 to 2y. X equals 2y is the same as y equals 1/2 x. So y equals 1/2 x, something like that. So x goes from 0 to that curve, as y goes from 0 to 1. So this is x equals 2y. So this is going to be the point 2, 1. Okay? And then the second integral is from 1 to 3, 0 to 3 minus y. Okay, so now x is going to 3 minus y, which is the same as y equals 3 minus x. And let me just do that over here for just a second. So x is going from 0 to 3 minus y. Okay, so this is x equals 3 minus y. So x goes from 0 to 3 minus y. But y goes from 1 to 3, so it's not this whole thing. It starts here at y equals 1 to 3. So it's that piece up there. And this would be the point Y is 1, X is 2. Okay? Now, we're putting these together. So if I take this picture and put it over here, this is the 0.21, this is Y equals 1. We're going to go up to 3. This, again, is Y equals 3 minus X. So the region that they're integrating over is this whole thing. Okay? So if we're going to switch it and go dy dx, so I'm looking at it upright now, I don't have to break it into two intervals. If I'm to switch this and go dy dx, we got alpha of x and y, dy dx. We go from the bottom curve, but solving for y, so 1/2 x, to the top curve, which is y equals 3 minus x. As x goes from what? I just want to see if you guys are all awake, and I just found out that you're not. As x goes from where?
0 to 2.
0 to 2, good. You gotta work too. Alright? Alright, so 3 in a row of switching, so that needs a little work, right? Does that feel a little better? Okay. Anything else from 15.3 before we? Okay. 15.4. 25 and 20. Okay, so this is polar coordinates, which might have gotten a little more clear when we did cylindrical coordinates, because it gave us more practice. By the way, you're not going to take any sort of formal break, so take a break whenever you need one. Okay. 20. Alright, so we're supposed to find the volume. Okay, so before I even do anything else, let me remind myself, because my brain has been doing triple integrals. The volume is going to be f of x and y dA. But that's if you have, something like this, and you're finding the volume underneath it. There were a couple problems in your homework where you actually had to find the volume and you had an upper surface and a lower surface. If it's that, then your volume would be the upper minus the lower dA, just to kind of make sure that's clear, because you can do this type with double integrals too, but you got to do upper minus lower. And I know there were a couple of them in the homework, but most of the reading about it was the ones that go all the way to the xy plane. Alright, so 20 says below the paraboloid and above the xy plane. So below the paraboloid, z equals 18 minus 2x squared minus 2y squared. That's 18 minus 2 times x squared plus y squared. So that's we should recognize that that's a paraboloid that opens downward. And you don't have to graph it to get this, because they already said go below there and above the xy plane. So even if you don't know what it looks like, we should be okay with that. So all the way down to the xy plane means that the volume is just going to be the double integral of this function. I'm going to go ahead and leave that 2 factored out just because I know we're going to be using polar coordinates, because they told us to. But if they didn't tell us to use polar coordinates, hopefully we would see at this point, I'm thinking polar coordinates because you got an x squared plus y squared in the integrands. And what does D look like? D is this intersection right here, right? How do I find out exactly what it is? I put z equals 0. That's where it intersects with the xy plane when z equals 0. So we would get 18 equals 2 times x squared plus y squared. So x squared plus y squared equals 9. So we get a circle of radius 3. So this is going to be 18 minus 2x squared plus y squared is r squared. dA is r dr d theta. R goes from 0 to 3, and theta goes all the way around.
So if they didn't give us this function, we would have to use a triple integral?
If they didn't, well, still though, they have to give us the function, otherwise, yeah, we could do it with a triple integral of 1 dv, but then when it came time to set up the limits of integration, and
Well, they'd have to give us one boundary, right?
yeah, we'd have to know what surface is. So this would go from 0 to that surface, and times dA over d. So, and then the very first step, we'd integrate with respect to z, we'd get a z and we'd evaluate it, we'd be right to here. So, you know, in case you haven't seen that yet, we've seen it twice here, that, you know, it feels like you're doing less work because you're only integrating one instead of some complicated function. But it's the same, doing a double integral or triple integral is the same. All right, I know this one is not in your book, somebody want to throw out their even and see if we got it?
81 pi.
81 pi? And I get some agreement, so probably that's right. Except for some of you all work together, so you might be cool.
There you go.
Okay, let's see, so that's 20. 25, we're looking for above the cone and below the sphere. 51.4. Above the cone, z equals radical x squared plus y squared. And below the sphere of radius 1, okay, so again, a snow-cone kind of thing. And we're trying to find the volume of this using double integrals. So this is what I was saying earlier. If you're going to use double integrals, you have to integrate a function. You integrate top surface minus bottom surface. So that's going to be the green surface, but I got to solve for z. So that's 1 minus x squared plus y squared, if I put it in parentheses. And I have to subtract the bottom surface.
But that's still, again, it's still a triple integral. You're just skipping writing it down.
Well, yeah, it's the same as if we were going to do it as a triple integral.
I know, so like on the test, if you ask me this, and I do a triple integral,
If I ask you to set it up as a double integral, though, so there are problems. Well, in fact, you can look at the sample test. There'll be problems where I'll say, okay, find the volume, all these different ways. I want you to do it as a double integral, which means you have to know there's an integrand. I want you to do it as a triple integral in cylindrical. I want you to do it as a triple integral in spherical. So one problem set up lots of different ways. So if I ask you to do it as a double integral, you need the top surface minus bottom surface in there. Make sense?
yeah, it's just the triple integral, skipping a step or writing it down.
Right, I understand that, but, you know, if our goal was really to just find the volume, we just set it up one way to the easiest way. I just want to make sure you can set it up all the different ways. And this one could also be done as a solid revolution from 5A, for that matter. I didn't put it on your test, so I can tell you. One test recently, I gave a problem where I had them find the volume of the sphere, like 4 different ways. You know, so spherical coordinates, double integral, triple integral, rectangular coordinates, solid of revolution. One of the ways I let them do is just using the formula 4/3 pi r cubed, just, you know, kind of what are all the ways you know how to find this volume. And so for that example, of course, if I were going to find the volume, I wouldn't use calculus at all. But just to see if we can set it up all the different ways. All right, so a lot of people forget when they're doing a double integral, they need an integrand there. So I want to point that out. Now we need to figure out what region we're integrating over. And so we look at the intersection of these two. And if I look at the intersection of these two, for instance, I could substitute z into there. I get x squared plus y squared plus this thing squared equals 1, so 2x squared plus 2y squared is 1. So x squared plus y squared is 1/2. Okay, so I get the circle of radius square root of 1/2. That's my d. My d is x squared plus y squared equals 1/2. Circle of radius square root of 1/2. Okay, so if I'm going to do this in polar, which they asked me to do, I have to transform the integrand. So that's going to be 1 minus r squared. And then this is square root of r squared, so that's r. dA is r dr d theta. R goes from 0 to radical 1/2 as theta goes all the way around. Okay, that's okay to integrate. R times this one, r times radical 1 minus r squared, and then minus r squared. So this one you use substitution, and this one corrected. Okay. All right. Anything else we'd like to invite for?
Professor, so for number 25, if we want to do like in triple integral, how do I set the domain of it?
If you wanted to do it like what?
Triple integral?
Triple integral? Okay, so if you wanted to do that one as a triple integral,
So the domain for the z, like on the top it should be the paraboloid and the bottom should be the cone, right? And then we have like the circle, and then we find x and y. Okay, I think I got it.
you got it? You don't need to see it then?
Maybe if we can.
Okay, so you can do this. So the volume of this, volume is the triple integral over the solid of dv. And how many ways are there to do this? There's dx, dy, dz, every possible way. That's 6 ways. Plus cylindrical coordinates, plus spherical coordinates. So lots of ways we could go there. You want to see it? Let's just see a couple of them. How's that? I think it's good practice. So if I said, I don't know, how about, well, let's just do what you were just saying, dz, dy, dx. So that would be,
So we solve for z.
solve for z. So z goes from bottom surface to top surface. So it's always small to big. So z would go from radical x squared plus y squared to the green surface. When we solve that for z, we get radical 1 minus x squared minus y squared. Okay? And then we project down, and the projection down is that. That's the circle x squared, plus y squared equals 1/2. That's a 1/2. So y would go from, this is y equals radical 1/2 minus x squared plus and minus. So y would go from the bottom half of that circle, we could use symmetry here, to the top half of that circle. As x goes from left to right, those are radical 1/2s. So minus radical 1/2 to radical 1/2. Okay? Now notice if I integrate this after the very first step, integrate with respect to z, I get a z, put this in, minus put this in. We're right here. That's what Tanner was saying is, well, you know, I mean, it's the same thing either way. Yeah, it is. Okay? Let's do the spherical coordinates. So if we're going to do the spherical coordinates, dv becomes rho squared sine phi. There's that factor there. d rho, d phi, d theta. So when you're looking for rho's limits, you just think about shooting an arrow out from the origin. Here we start in the solid, and any arrow that I shoot is going out the green surface. So rho goes from 0 to the green surface. The green surface in spherical coordinates would be rho squared equals 1, so rho equals 1. So rho just goes from 0 to 1. Then phi does this. You know, we're here, and then we're here, and then we're here, and then we're here. So phi goes from 0 to this angle here. That's this standard cone. So pi over 4. But I showed you in class, and I can remind you if you need to see it, how we find that if it's not the standard cone. And theta goes all the way around. So it's not just the front half or the right half, it's the whole thing. So 0 to 2 pi. That's probably that and that's probably the easiest way to do this one. This one's pretty easy too. But any sort of rectangular coordinates of this is going to be a mess because these equations are messy to integrate in rectangular coordinates. Questions?
That's for question number 15. I mean, we need the function as 1 there instead of using any others.
Let's see.
Yeah, just want to do the integral. We have the domain.
Oops, I lost it. Question number 15?
Yeah, 15. It's a rose pattern. The one loop of the rose.
Yeah, because you're finding the area, so you're going to do the double integral of 1 dA. So the integrand is 1.
Yeah, because sometimes we put the function there. And
Then you're finding volume. For a double integral, if there's a function there, you're finding volume or some other application. For a double integral of 1, you're finding area. Okay? So I don't know if you remember, but I put it in both of the classes, you know, single integral of 1 is length, the single integral of a function is area. Double integral of 1 is area, double integral of a function is volume. Triple integral of 1 is volume, triple integral of a function is not a physical, a geometric application. That's sometimes good to go back and look back at and kind of organize your thought process, but does that help with your question?
yeah, am I right with that? Thank you.
All right, 15.4, 15.5 and 6. Teach. Yeah.
Can you show how to find parallel forward?
Oh, sure. So, and I'm glad you asked if you weren't sure because typically on a test, if I give you a column, it's not the pi over 4 one. Okay?
Wow.
So it's good to know. And so his question is, how do we find this angle right here? And so what we do is we look at, what we want to do is we want to look at this right triangle, get some information about this right triangle, and then use trig. So what kind of information do I have about that right triangle? Well, in this case, for one, this one goes all the way out to rho equals 1, so this has to be a 1. They don't all do that, but this one goes out to 1. What else do we know? Yeah, this x right here is radical 1/2. Radical 1/2. So that's all we need to know in order to, well, you just need two sides, you can get the angle. But if you wanted the z value also, you could finish what you were doing here when we were looking at the intersection. X squared plus y squared is 1/2. Putting that in there, we get the z value. Z is radical 1/2, so you could get that here too. So, you know, we had those two, right? So that's opposite and hypotenuse. So the sine of phi is opposite over hypotenuse, so 1 over radical 2. So phi is, I'm going to go ahead and write it this way. The inverse sine of 1 over radical 2, that we should know is pi over 4. But it's possible that it's going to be one we don't know exactly. And then we would put it in our limit as inverse sine of one we don't know exactly. Just choose an inverse sine.